Good morning, everyone. I'm Swetha, and today I will be talking about our work on the role of extreme and critical curves on the bifurcation structure of one-dimensional maps. For our work, we have considered the mod 1 sine circle map, which maps the circle to itself. The sine circle map has two parameters, and despite its simple structure, it exhibits complex dynamics such as quasi-periodicity, chaos, period adding behavior, etc. The sine circle map has been used to model several real-world phenomena such as cardiac arrhythmias, Josephson junctions, etc. This is the sine circle map, and as we can see, it has two parameters, omega and k. Omega is the bare rotation number, which means that omega will be the rotation number of the map in the absence of the nonlinear sign parameter, and k determines the strength of the nonlinear term. The first step in studying the sine circle map would be to plot the two parameter chart. For this, we have considered the parameter ranges -1 to 1 for omega and 0 to 4 pi for k. We have considered 1000 points in between these intervals, and we have calculated the Lyapunov exponent according to this formula for each set of parameters omega and k. In this plot, the regions in black have negative Lyapunov exponents and they indicate periodic regions. And the orange shading indicates values of Lyapunov exponent close to zero, which is quasi-periodic regions. And the blue-green shading has positive Lyapunov exponents and therefore exhibits chaotic behavior. Next, we calculated the critical points for the sine circle map by setting f dash of x is equal to 0. We have found the critical points of this form where p indicates integers. As we can see from this, the critical points exist only for values of k greater than equal to 1. That is why k is equal to 1 is called the critical curve of the sine circle map, and it represents a boundary between the periodic and chaotic regions in the parameter chart shown before. And as we can see, chaotic behavior is seen only above this critical curve. A new concept was introduced by Professor Medrano's group, and this is called the extreme curves. When a critical point xi maps to the critical point xj after k iterations, we get the extreme curve eij after k iterations. And an interesting property of the extreme curves is that the K1 iteration extreme curve Eij and the K2 iteration extreme curve Eji intersect each other in a region of the parameter plane having period K1 and K1 plus K2. So we have analytically computed the one iteration extreme curves of the sine circle map, and it has been shown in the slide. However, for higher iterations, we will have to solve equations of these forms, which is difficult, and which is why we have computed the extreme curves numerically using root finding methods, specifically the bisection method, and we have plotted the results on the parameter space. And for example, the light green and dark green curves indicate the one iteration extreme curves, and they intersect in a region of period 2. Another important uh, uh, tool to study the sine circle map is the rotation number. A rational rotation number indicates periodic behavior, while an irrational rotation number will indicate quasi-periodic or chaotic behavior. Rotation number is also used to identify frequency locking regions. This is the formula that is generally used to calculate the rotation number rho. For the sine circle map, we can calculate the rotation number along the critical curve k is equal to 1. And the rotation number is plotted as a function of the parameter omega, and the result is shown here. This structure is called as the devil's staircase, It is continuous, monotonically increasing, and also has a fractal structure, which means that as we zoom in on any of the region of this curve, we will see a similar staircase structure. The plateaus in this curve indicate frequency locked regions, which means that for small shifts in parameter range, the rotation number still remains the same and rational. However, this rotation number has only been calculated along the k is equal to 1 curve using this method. For k greater than 1, the map is non-invertible and can have chaotic behavior. In chaotic regions, the rotation number cannot be calculated using the limit formula shown before because the limit does not exist. Therefore, we have proposed a new method to calculate the rotation number in these regions of the parameter space. We start with some initial condition x0 and then we perform 10,000 iterations to get rid of the transients. After this, we check for periodicity of up to 100 periods. Then we calculate the rotation number as the ratio of the number of returns of the trajectory to the period that has been found. Here we have plotted the rotation number calculated using the newly proposed method on the right, the return method, and we can see that it is same as the rotation number calculated using the regular method. Next, in order to explore the parameter space, we identified a region of the parameter space which shows an interesting behavior, which is called period adding. As we can see on the plot on the left, the red line indicates the 3 plus extreme curve and it passes through regions of periodicity which increase by a value of 2. Like for example, the dark blue region has a period of 6, the orange region a period 8, the off-white region has a period 10, etc. A zoomed in picture has been shown on the right, and here we have characterized the parameter space using Lyapunov exponents instead of periodicity, and we can see the periodic behavior along the extreme curve. To understand this further, we have also plotted the bifurcation diagram for these two plots, and we can clearly see the period adding behavior. We can see the regions of period 6, 8, 10, and in the zoomed in region, 10, 12, 14 periods are also visible. And as we zoom in further, we will also be seeing higher order periods like 16, 18, etc. So we thought it will be interesting to find the rotation number along the extreme curve in this period adding region, and we obtained an interesting result. This is the rotation number plotted as a function of k along the extreme curve, that is the red line shown in these plots. And we can see that we are getting a constant rotation number of 0.5 in this region for periodic values and 0.49 in the chaotic regions. To validate our results, we also plotted the cobweb diagrams. We chose points along the extreme curve in regions of different periodicity. And then we have plotted the cobweb diagram. For example, we took a point on the extreme curve in the period 6 region. And as we can see from the cobweb diagram, we can clearly see that it has a period 6 and there are like 3 rotations, which is why we are getting this rotation number of 3 divided by 6, which is 0.5. The same is true for the period 8 region, period 10 region, etc. And we also chose another point in the chaotic region, and here we can see a highly dense cobweb plot. But still, like we can see that in this whole region, we are getting square attractors. So in conclusion, we can see that studying different regions in the two parameter chart reveals very different and results and interesting results about the one-dimensional maps. And the extreme curves especially play a very essential role in studying the maps. Recently, it has been shown that the values of the uncertainty exponent and exterior fractal dimension calculated along these extreme curves are different from the values calculated from different other parameter curves, like for example, the critical curve. But this has been shown in the case of the logistic Gauss map, and it will be interesting to see if this behavior is also replicated in the case of the sine circle map, which will be studying next. Thank you.